Hi Mary, it's been a while. Well, I think it's actually been since I lived in East Lansing, but I've started doing video tutorials for some of my students. I'm working at Macomb Community College now, and so I thought in response to the question that you posted on Facebook. So, first and foremost, let's make one thing absolutely clear right now. Your math teacher talking about the rectangular parallelipiped, that's a fancy way of saying the box. So we're going to say in our box that the length of the base is A, the width is B, and the height is C. What we're going to do is come up with a formula for how to find the length of the diagonal of the parallelipiped. So what we're going to do is actually set this up in a three-dimensional coordinate system. Here's the z-axis, here's the y-axis, and here's the x-axis, and y, and z. Alright, so this box, I'm going to use dashed lines for it. This box, we have a face over here, we have a face over here, in the xz plane, and finally we have one over here, in the xy plane. Stuff not attached to a plane, I'm going to draw this in red so that we know that it's coming out at us. Like so. So what we're interested in is an expression for the distance from our origin, right here, out to this point right here. Now the way that we're going to do this is to point out that all three of these planes, or rather all six of these faces of the box, are all perpendicular to each other. So for example, this line right here connecting the xy plane with the point that I have in here is parallel to both of the lines that are in the xy plane. Moreover, they're also perpendicular to anything that's in the xy plane. This is good to know because we're going to draw something in the xy plane. We're going to draw something right here, and we're going to draw something right here, and we're going to draw something right here. Now, even though the angle is kind of awkward, my hand is very unsteady, the x-axis is perpendicular to this line coming out of the x-axis. Now, the way we had them defined over here is that this distance was A, and this distance was B. Using the Pythagorean theorem, we can figure out what this distance is over here. For now, we're just going to go ahead and call it x. I'm going to draw one more triangle in here that'll also be of significance to us, and we're going to draw the second one in red. The second one is this side right here. I'm going to connect that with the side labeled x, and I'm also going to connect that point with the origin down here. Now the reason that I'm connecting those is because this diagonal from the origin over here along x is perpendicular like so. So given that these are perpendicular, what we wind up with is a pair of right triangles. Ultimately, we want to get this quantity z. Now I'm also going to label this side over here as c based on how it was drawn up here because that's the height of our box. So what I'm going to do is set up our good old-fashioned Pythagorean theorem. There was a comment on your Facebook that said a squared plus b squared equals c squared, you're welcome. That was actually very accurate as to what we're doing here. So first off, actually we'll stick with red for this one, I'm going to come up with an expression for the right triangle that is in red, connecting the hypotenuse z with the legs c and x. So that gives us the expression c squared plus x squared is equal to z squared. We're interested in the expression for z. The angle in black here, down here, is, well let's see, a and b would be the legs because they form the right angle, and x is the hypotenuse. So that gives us a squared plus b squared is equal to x squared. But we're interested in getting an expression for z in terms of just a, b, and c. So what we're going to do is now we're going to plug this x squared in to this expression right here. So I'm going to recopy the equation in red. That's going to look like c squared plus, and instead of referring to it as x squared now, we have the expression a squared plus b squared from the substitution. This all is equal to z squared. Now we are, of course, interested in solving for the distance z. To get rid of our square, we take a square root of both sides, which means that we'll have z is equal to the square root of, and I'm going to reorder it so that it's in alphabetical order. What we wind up with is that z is equal to a squared plus b squared plus c squared, where a, b, and c are the 3 dimensions that were given to you in the problem. I sincerely hope that this helps and that it clears things up for you, and now I get to try to figure out how to send this to you. So, I'll see you next time.